one knapsack problem using the dynamic programming approach. So can anybody tell me what is knapsack problem? We have already studied about that. I want someone to tell me what is knapsack problem.
मैम एक पर्टिकुलर वेट होता है, उसमें से हमें मतलब पिक करना होता है और मैक्सिमम आउटपुट मतलब प्रॉफिट गेन करना होता है उन वेट
Hmm.
से.
So इसमें क्या है कि that means we it is like that we have one bag जिसका एक फिक्स्ड वेट है, राइट, और हमारे पास मल्टीपल आइटम्स हैं और जिनके साथ कुछ प्रॉफिट एसोसिएटेड है, right? So for all these items, some profit is being associated, and we have to fill the bag with these items in such a way that that way, because the bag is having a limited capacity, so we cannot put the weight beyond that particular capacity, and we have to maximize the profit along with that. So these are the two objectives, we can say. One is maximization of the profit, and second one is minimization of the weight, or you can say just keep the weight as it is, because we cannot increase the weight of the bag. तो हमारे पास क्या है कि जो, और इसमें when we say what is the meaning of 0 1?
मैम हम पहले मतलब फ्रैक्शंस में भी ले सकते थे, लेकिन अब फ्रैक्शन में नहीं ले पाएंगे वेट्स.
हाँ, मतलब इसका मतलब है कि knapsack problem is of two types. One is 0 1, another is fractional. 0 1 का मतलब है कि कोई भी जो आइटम्स अवेलेबल हैं, we cannot take them as the fractional item. उसका कुछ पार्शियल आइटम को नहीं ले सकते हैं. जैसे मान लो कि हमारे पास किसी म्यूजियम में बहुत सारी आइटम्स हैं, तो म्यूजियम की जो आइटम्स हैं दे आर लाइक यू कैन से, कोई डिफेंस का म्यूजियम है तो वहां पे आर्म्स वगैरह हैं, तो हम आर्म्स को तोड़ के तो नहीं ले जा सकते हैं. So we can consider the items such that we cannot take up the partial or the fractional part of that. So in that case, either we will be taking the complete item or we will not be taking the complete item. And in case of the fractional knapsack, you can say that we have items like grains hai hamare paas. So in that case, we can take the partial grains, partial fruits. So if we have such kind of items from which we can extract the partial part, so we call them as the fractional knapsack problem. कि अगर 5 किलो 5 kg मैंगो है तो उसमें से हम 2 kg भी एक्सट्रैक्ट कर सकते हैं, right? So that is called as a partial knapsack problem, and where we cannot break down the items into the fractions, or we cannot take the partial items, we call them as the 0 1 knapsack problem. So now we are going to study the 0 1 knapsack problem, how to find out the solution using the dynamic programming approach. So given a knapsack with maximum capacity W and a set S consisting of n items, each item I has some weight Wi and benefit value, that is called as a profit, which is associated with this. So here we are assuming all these are the teacher values. Now the problem is how to pack the knapsack to achieve maximum total value of packed items. So this is what we have already done in the greedy algorithms. We were trying to find out the solution. So whenever we were finding out the benefit per unit weight values, so we were computing the value by computing the benefit per unit weight, and then on the basis of that we were trying to fill up this particular knapsack when we were using the greedy algorithm. Now, in order to solve the same problem using the dynamic programming, what do we have to do? So the optimization criteria, as I've discussed, that is to maximize the benefit value while maintaining the knapsack weight less than or equal to its capacity. So maximize, so if we have to write this as a maximization optimization problems, so we can write it mathematically as maximize the total profit subject to the weight, knapsack weight we say, that is less than equal to its total capacity. So what is the naive method? The brute force technique we say, that is to consider all 2n possible. See, n is the number of items. If we have 4 items, how many possible cases may be there, in what subsets we can create, and we can find out the solution. So one way is to find out all the possible subsets of n objects, choose the one that fits into the knapsack and maximize the profit. But see, this kind of solution is good where the value of n is less. But for the large values of n, such kind of solutions are very time consuming, and we may not be able to get the solutions in the polynomial time. So you can say the brute force approach is not the appropriate approach for solving large size problems, as its running time is going to be 2 power n. Then optimal substructure. If the items are labeled 1 to n, then a sub-problem would be to find an optimal solution for Sk, where items are labeled as from 1 to k. So that means, see, we are trying to find out, as we said, in order to find the optimal structure, the optimal final structure. If we are able to find the optimal substructures, then combining together, we can find out the optimal structure for this kind of problem. So here you can see this is the recursive formula for the sub-problems. Recursive formula for the sub-problems. Here you see that B, K, W, K and W, they refer to the row value and the column value. So here you can say B of K minus 1, comma W is, that means we are going to create a table that you can say we are going to apply the dynamic programming, and we are going to create a table of items and their weights, and we are going to associate the benefits associated with that. So in order to fill up that particular table, what we are going to do, we are going to apply this recursive formula. So we are going to study this with the help of an example. So if Wk is greater than W, then we write B of K minus 1 comma W. Otherwise, in the else case, what do? We take the max of B K minus 1 comma W. So and comma B of K minus 1 comma W minus WK plus BK. So this is, you can say, a formula that you will be able to understand when we will do an example along with that. So here telling that the best subset of Sk, that is total weight W, right? So the best subset of Sk minus 1, that has total weight W, or the best subset of K minus 1, that has total weight W minus WK plus the item K. So this is how we are going to compute the best subset of this particular item. So how do we find out see the best subset of Sk, that is the total weight W, either contains an item K or it does not contain that particular item. So in the first case, what do? We say Wk is greater than W, item K can't be a part of the solution, since if it was, the total weight would be greater than W. So that means we have to see that if the weight of that particular item is greater than that, let us say the capacity of the knapsack is 2 and the weight it is coming is 3. So we cannot accommodate this particular item, because otherwise it will increase the weight, which is unacceptable because our knapsack cannot accommodate that. So that means this case won't be applied. So we will look at the another case that Wk is less than equal to W. Yes, then the item K can be in the solution, and we choose the case with the greater value. So here you just you can see the here it is the pseudocode for solving this particular problem. For W is equal to 0 to W, small w weight, we say all the weights which are, so what we are going to do when we are trying to apply, see, as we said in the dynamic programming, we find out all the possible solutions, but along with that we are trying to reduce the complexity also. So that means, and how do we reduce the complexity? By through the concept of memorization. So here we see we are creating an array of 2D array. We are where we are putting the weights of the knapsack. If the capacity of the knapsack is 8, let us say, so we will be taking the capacity up to 8. That means from 0 to 8. So then similarly, when if the number of items is n, so you can see we are creating the array with up to the number of items n, and initially we are assigning, initially there is nothing in the knapsack, initially there is no item, right? So the we are going to assign 0 to it. So for, and then what we move, because it is a 2D array, so we are taking the for loop that iterates from 1 to n for the number of items. Another array which iterates the weights from 0 to maximum capacity, that was of the knapsack. So and then if we can compare, if Wi is less than equal to W, that is, item can be a part of the solution or not. So we will see, we will pick up the first item. For every item we have certain weight and we have certain profit associated with that. So if the weight of item is less than that, then it can be a part of the solution. So if Bi, that is the item, we say is, if Bi plus Bi minus 1 comma wi minus wi is greater than this value, then only we are going to assign this. So this particular formulation, which is not, you can say, we won't be able to understand without the help of the example. So I will take up one example first, and then we will see, go back to this particular formula that we have seen, so that we are able to understand it very clearly. So let us run this algorithm that we have seen. So let us say we have n is equal to 4, that is the number of elements of the number of items, and w is equal to 5 is the maximum weight, that is the capacity of the knapsack. So let us see these are the four elements which are, you can say, four items which are associated. Or you can say the first element represents the weight, and the second element represents the benefit associated with that. So as we see, as we have done in the algorithm, we see we have created a 2D array. So on one side, you can say the columns represents the items, and the row, rows represent the items, and the column represents the weights, that is 0, 1, 2, 3 up to 5. 5 was the maximum capacity. Here you can say W, the weight. So the maximum capacity of the knapsack, and number of items are 4, which we have shown over here from 0 to 4. So what do we do for the first, as we start from that particular algorithm, we assign the 0 values. We have assigned the 0 values of all the items which are there in with this particular capacity. So, and the first row and the first column. So all the items in this particular this and all the weights over there, we have assigned the 0 values. Now let us start with the first item. So when we start with the first item, here you see the first item has a weight of 2 and its benefit is 3. So if we have a capacity of 1, see, when we see the column values of 0, 1, 2, 3, 4, 5, they are indicating the capacity of the knapsack, right? So whatever is the maximum capacity, see, this is a way to solve this particular problem using the dynamic programming, that we are computing the solutions for all the subsets, right? So at every stage we are going to make a decision, because it is based on the principle of optimality. So we say that if we consider the capacity as 1, our item that we are saying its capacity is, its weight is 2, so the knapsack cannot accommodate the item whose weight is 2. So, and the knapsack weight is 1, so we cannot accommodate it over here. So we will take its initial value of 0 only, and then the item, the first item will be accommodated over here. So here we have written, see, the because the capacity is already indicated using the index value, right, that is 2. So we have marked here the benefit which is associated at this particular stage for this particular weight. So here you can see we have taken this particular value of the weight. Now if we move further, we are moving the column wise, right? If we move to the next capacity, so capacity is 3, but we have already, we don't have any other item over here. So because 3, 4, 5, right? So if these are the capacities of the knapsack, so all these capacities are greater than 2, so they can accommodate this particular weight, right? So we can write them as it is, right? So now as we move to the I is equal to 2. So here you can see on correspondingly all the values have been updated on the right hand side. These values of all these have been taken. So B is the benefit which is associated, Wi is the weight, the capacity, and then another W is the you can say the iterative value of W, that is the capacity of the knapsack, and that is the current value of the item that we have taken, and then we see the difference, it is 3, right? So now we move on to next, right? So here we see, as we move on to the second item, because if you see the weight of the second item is 3, right? 3 and 4, here you see I'm referring to the item that is given on the top. So the second item is having weight of 3 and benefit of 4, but if our item is having weight 3 and the since 0, 1, 2, so they are the knapsack weights, so the item which is having a weight of 3, it cannot be accommodated in the knapsack of weight 0, 1 or 2. So the values, so the previous values will remain same, as it is. They won't be changed. The new value that will be updated is that will be over here. So 4 is the benefit which is associated with the second item. So we have updated this over here. Now here you see one thing that you have to remember, that when we are computing the values of the previous ones, so whenever we have reached to the second item, we will always be considering all the previous items also which can be accommodated. So here you see in the previous ones also, since so if we see go back and see to the previous row of item 1, so item 1 row, since we could accommodate in the benefit 3 is associated with the item 1, that is whose weight is 2. So in that case 3 can also be accommodated since it had a value of 0 before that. So 3 plus 0 is 3 only, so that's why we have repeated that over here. Now here you can see, if we see we now the item 3, the knapsack weight has 3, so the benefit associated with that is 4. So we have written this value of 4 over here. Now if we see the both of these two items, so their total weight is 5, right? Since their total weight of 2 plus 3 is equal to 5, so but the knapsack capacity has 4, so we will be repeating this value, right? Because knapsack weight of 4 cannot accommodate two of these items, right? But a knapsack weight of 5 can accommodate both these items. So because 3 plus 2 is 5, this is the total knapsack weight, and the profit that will be associated with that will be 3 and 4. So we can write the profit as 7 over here, right? So if in case of any doubts, you can stop me at any point of time, because otherwise you won't be able to understand. So similarly, now we take up the item 3, that is whose weight is 4 and whose benefit is 5. Since its weight is 4, so this item cannot be accommodated at these particular stages, so their values will be as it is copied over here. So we move on to 4. Since its weight is 4, we can have only here, so its benefit associated is 5, so we are writing over here. Now we have all the items before that. So we have 3, you can say the total weight, 3 items. The first item, second item, third item. So out of these, the total capacity of the knapsack is 5. So either we can have first 2 items, 3 plus 2 is 5, or we can have only one of these items. So when we see all these things, so we will see the which one is giving us the maximum benefit. So the maximum benefit is given if we take up the first 2 items rather than the second item, that is 4. Right here it is, if we take only the third item, so because we have a knapsack capacity 5, so if we take only item 5 in this particular capacity, we are going to get a benefit of only 5. But if we put these first 2 items, then the total benefit will be 3 plus 4 is equal to 7. So what do? We take up these 2 items in this particular capacity. So similarly, what do? We are going to do the particular, all these things, same thing. So since it has a weight of 5, so all the values 0, 1, 2, 3, 4, they are repeated, because this item cannot be accommodated in these particular knapsack weights. So what do? We reach to the last one. In the last one, again we compare with the previous one, all the combinations, which one is the best. So if we take only one item, that is 5, 6, so, right? So in that case, the benefit is only 6. But if we take again the same combination, which combination can be accommodated in a knapsack of weight 5? So the same one can be accommodated, and we can get the maximum profit, that is 4 plus 3 is 7. See, if we take the second and the third item, we are going to get the profit of 9, but their total capacity is 4 plus 3 is 7, which is beyond reach, which will be greater than the maximum capacity of the knapsack. So we have to see, we cannot accommodate the weight greater than the capacity of this knapsack, but we want to maximize the profit. So what do? We take these 2 items only. So this is how we try to solve this 0-1 knapsack problem using the dynamic programming. So the problem is not yet solved. Now from this particular table, how do we find out which items are being accommodated into the knapsack and which items are not accommodated? That means out of the 4 items, which will be included and which will not be included. So we are going to study this in the next class. So the technique or the algorithm for finding the items which will be taken in the knapsack is as follows. So here we are assuming like these are the two you can say the variables which we are going to use for the iterating over the number of items as well as the weights. So if BIK we know because it is a matrix, so we say that B is a matrix that we have created this one. So in this particular matrix, I is representing the rows and W is representing the columns. So if BIK is not equal to BI minus 1K, so here you see our column is kept fixed and we are going to start from the last cell of this particular matrix. And from there we will see if the item which is there, the you can see the benefit, because in the matrix we have assigned the benefits only. So if the benefit which is there in the last row and the benefit which is there in the previous row in the same column, if they are same, right? Here you see here, if we see that you can see if I see the cell number 35 and the cell number 45, in the cell number 35 as well as in the cell number 45, the benefits are same. So that means if they are not same, we are saying if this is not equal to this, only then the ith item will be kept in the knapsack. That means if these values are same, if these values are same, that means the because if we start from the last item, so that item will not be kept in the knapsack. So this is how we are going to consider that which particular item will be kept in the knapsack and which one will be discarded. So if these values are not same, then we will keep the item I in the knapsack and then we will reduce the row number to -1. Along with that, we will be reducing the weight, because in the knapsack we have to take care the item which is kept. Let us say we are keeping the last item in the knapsack. In that case, we will have to reduce the weight of that item from the total weight of the knapsack, so that we can make sure that the other item which will be kept in the knapsack, its weight should be equivalent to the only weight that can be accepted by the knapsack. Otherwise, what we will do, we will just keep on decreasing the value of the row and we will keep on moving upwards, right? So that we are able to find out at what stage the items which are there in the same column, they are different. So here you see, here we are using the different variables. I is referring to the item number and K is basically the column number, as we have seen, BIK. So BI is the benefit which is associated with the particular item that we have chosen. And then the BIK is, here you can see the value of BIK. BIK here, I is equal to 4. So, and K is equal to 5. Then BIK is equal to 7 and BI minus K 1, that is 3. 3 comma 5 is also 7, which we can see from here. So these two items are 7 and the algorithm says if they are not equal, if they are not equal, only then we will be keeping the ith item. This is the ith item, the last fourth item. Only then we will be keeping the fourth item in the knapsack. So WI is basically the weight of the fourth item that we have seen. So I'll just trace and see here. You can see the last item. We have 4 items out of these 4 items we have to choose. The last item has a weight of 5, then 4, then 3, then 2. Then you have to just remember this when we are going through this example. So that means if they are same, what do? The algorithm says just decrease the value of the row by -1. So we decrease the value of the row by -1. We have moved to the third item. Then value of K remains same because we have not changed the value of the column. Then BI is the profit that is associated and WI is the weight of the third item. That was 4. So here you can see again BIK, that means now BIK and BI minus 1 KR, BIK is 35 and BI minus 1 comma K is B25. So if we have the values of the 35 and the cell number 25, they are again same. So the algorithm says we have to reduce the value, we have to just reduce the value of the column, sorry, the row to -1, and we are not going to include even the third item in the knapsack. So we move upwards. Now again we have moved to the second item again. So when we move to the second item, in that case you see the weight of the second item is 3, and BIK and both these values are not same, because the BIK, that is the second one, so the 2 5 value is 7 and the 1 5 value is equal to 3. So that means if these are not same, what we are going to do, we are going to include the second item into the knapsack, as the pseudocode is also shown over here. If BIK is not equal to this, then mark the ith item the knapsack, I is equal to I minus. So we have marked so here we are marking, basically we are marking that the second item is kept in the knapsack, and after that what do? We reduce the value of I to I minus 1, and K is equal to K minus WI. That weight of the item is 3. So we are reducing this particular weight from the weight of the knapsack, which is 5. So here what do? 5 minus 3 is equal to 2. So here that is being done. K minus WI is equal to 2. So that means that now we are left, the capacity of the knapsack that we are left with now is only 2. So what do? We move on to the next item. So we have marked the second item to be in the knapsack. So now we move on to the next item in the knapsack. So we have moved to the second item. Now here you see, since we can include only this much of weight, that's why see K is equal to W1. Here you see K is equal to K minus WI is equal to 2. So that means this is the only weight or less than that we can accommodate in the knapsack. That's why we have directly moved the arrow from this fifth column to the second column, right? 0 1 2. So the column with the whose weight is 2. So right, we move from here. Now you see, so its value is 3. So again we see the values of BIK. So the BIK, that is 1 2 is 3, and BI minus 1 comma K is equal to 0. That means these are not equal. So we can also include item 1 into the knapsack. So when we see that, when we include this particular item in the knapsack, and then we see we are left with a weight K minus WI is equal to 0. So that means the weight or the capacity of the knapsack is now left, we are with 0. That means we are done. We cannot have more items into the knapsack. So finally we can say we can only have these items into the knapsack. So the optimal knapsack should contain only 2 items, that is item 1 and 2. So this is how we apply the dynamic programming approach for solving the 0 1 knapsack problem.